So as stated earlier, so we are going to be looking at a couple of very important concepts before we move back again to demonstrating more on weaker. And one of the concepts, very important, we've mentioned then, is the concept of hypothesis space, where I mentioned that every algorithm has its own hypothesis space, so called designated as H. So two algorithms doesn't share the same hypothesis space, and each of them have their own unique one. And inside it, there are a lot of possibility, H1 to Hn. So the hypothesis space determines the functional form. It defines what are the allowable rules and functions for classification or regression. And so that, like I said, each classification or regression algorithm uses a different hypothesis space, as the case may be. Now, so this will lead us to the concept of inductive learning hypothesis, which I mentioned to Rhoda is really very important. It is stating that it is a kind of a summary of the way that machine learning really works. It says that if the hypothesis works for enough data, then it will work on new examples, which is why we usually divide our data into two, or as the case may be, we want to see what are the options we can use in checking out this. So that is why we are going to first of all look into evaluating models. So when you want to evaluate your model, you must have a way of checking is it okay or is not okay. But to do this, we have the essence of it that we want to look at the generalization capability. It's not just enough to train a model and you get higher performance accuracy on the training set, but rather we want to look at how can it generalize to the one that has not been seen before, this unseen data set. So what is going to be the performance when you expose it to this unseen one? These are the test data. This is called the generalization ability. So we need to ask the question, how well does a learned model generalize from the data it has been trained or it was trained in to the new test set? This is always our guide. In order to do this, we people look into how to check generalization abilities. Because yesterday we demonstrated in Weka, you can see that we have 2 or 3 options. We use division into 2, 70%, 30%. So today I want to quickly expose us to other available options of dividing your data. So to estimate the generalization error, we need data. We need data that is unseen during the training. So, like I said, we're going to make it very brief because of our time. However, further details, we can consult some of our earlier videos to check out more detail on this topic. Now, there are 2 major methods of splitting the data. The first one is known as holdout method. We call it holdout method. Holdout means you divide the data into portions, you use one of them to train the system, and you keep the other out. That is called holdout. In this holdout is divided into 2 types. We have where you divide your data into 3: training set, validation set, and testing set. And the second type, you only divide into 2. This is the very popular one. And any of the options you use, you are okay. However, if your data is sizable, you have a very big data, it's good to use this option. Divide your data into 2. You can use like 75% for training. You can use 15% for validation, and then another 15% for final testing. Some people call it publication testing. So either you use this or you use this, you are okay. So these 2, they are referred to as holdout method. That is, you use part of the data to train the model, you expose it to the algorithm so that you can get the model out of it. Because algorithm plus data, we produce model. So we can clarify that now. You see, model is the outcome of using the appropriate algorithm on the available training data. It will generate a model. Now, the next type of division is what we call the n-fold cross-validation. And this is often used when the data is very few. When you have very few data sets, sometimes we get like 16 samples from client. When you have only 16 samples there's no way you can divide it into 70%, 30%, because the data is really very small. In that case, we use n-fold cross-validation. It could be two-fold, it could be three-fold, as the case may be. Now, this is the old-out method. In the old-out method, I think we've demonstrated that yesterday in Weka. This is your full data, just divide into two, maybe 70% or 30%. It could be 80%, 20%. It doesn't matter. It depends. If you are using, let's say you are solving a problem that has been solved by someone earlier, and they use 70%, then you need to use 70% also like them, so that you can compare your work with them. You cannot use 70 and compare with someone who used 60. So you have to let your data partition be similar to what you are going to compare your work with. However, if you are the one that is doing it for the first time, then you have the liberty to use whatever option you want. 70%, 80%, but this is my own preferable option, 70 or 80. 90, I see is getting too much of the data for training, very little will be left for testing. However, some people do that. Some people go as far as having 60% for training, 40 for testing. But it's always good to have majority of the data for training, because you want the system to really get to know the system to be able to predict well. So this is the training set and the test validations or testing set, as this will be. So when you divide your data into two, this is what happens. You have your data, you partition into training set and testing set. So you build the model using the training set, and then you test on the testing set. The step 3, you need to evaluate the model using the testing set. So once you do the the model is generated. So you use the testing set now to check the prediction capability of your model, which is what we call evaluating the model. You want to check if what you have produced is actually okay. When you use the 3 partitioning approach, when you use the old out method with 3 partitions, that is, you have training set, validation set, and testing set. This is what you are going to have. You see, you have the data here. You partition it into 3. There's the training set here. There's the validation set here. These are inside the building of the model. When you have big data, I like this approach. There will be the testing set totally outside the building process. So when you train your data, you use the validation set to check if it is doing fine, and you evaluate it. Is it doing good? Yes, it's good. I finished building my model. If you have another data, which is the testing set, now you put it outside, you can finally, now you build the model, you validated it to make sure it is fine. Now you still have another thing outside, which is the final evaluation. It means we have evaluation 1, evaluation 2. This is when you use this option of dividing it to 3. Somebody might want to ask, but why do I need this trouble of 3 when I can use 2? Yeah, you can use 2. Just use training and testing. It's okay. However, for researchers, sometimes you have some very exceptions. Some few people, maybe very rare, they say they want you to use these 3 approach, divided into training, validation, and testing, and they have their kind of opinion on it that they always like it. But very few people, in most cases, you use training and testing set. No one raised any issue in as much as you have done the work in the right way. So, like I said, any of the 2 options are fine. However, if your data is sizable, it's a little bit big, it's always good for you to divide it into 3. But dividing into 2 is also okay. Now, this is the one we call the cross-validation. The cross-validation now. Cross-validation. In this case, you have your full data. You want to divide into, let's say, 3-fold. I want to use 3-fold cross-validation. 3-fold. It means you divide your data into 3 parts equally or near to equal parts. Let's say you have like a 100 data set, divide into like 33%. One will be a little bit more than the other. That's fine. So the first one is going to be used for validation, while all the remaining ones, you mark them together. We use it for the training set. Use it to train, use the small part to validate. Now you can see the validation is moving to the second part here. This part was the validation part before. We move it to join the training set. You can see the color. We use this one and this one for training, and this is the new validation. Once we are done with that, this is second time. The third time, this one will become training, then we use the remaining one for validation. We're going to see it in more clear form now. Let's look at this data. Look at this example. We divided our data into 10 folds. 10-fold. So if you have like 1,000 data divided into 10, that's going to be 100. So we have 100 here, 100 here, 100 here. So you use the first one for the validation or testing, while you use the remaining one from 2 to 10. It means 900 samples will be used for training. Next, the one that was part of the training before will become the testing. This one will become part of your training. You always use 900 for training every time. However, the portion will change. This one is now being used for testing. Next is going to be this one for testing. You use all of them, each of them for testing at each fold until you use the final one here, which means you're going to have 10 results. Result 1 up to 10. So to get the final result, you are going to add all the results together. You find the average. P1 plus P2 up to plus P10 divided by 10. That will give you the average of your result. Maybe you've got 97.5. This is called 10-fold cross validation. This is another way by which you can actually try to check the performance of your model. Is it doing well or it's not doing well? Now, so having said that about cross validation, we'll come back to that. Later we'll show an example in Weka after some time now. Now, another very important thing to note is, how do you now describe the classifier? Here we say you have to calculate the result. So what is the result you have to use? Briefly, when you are dealing with classification, so you are going to be talking for binary classifier. We have what we call true positive, false positive, true negative, false negative, the recall, the precision. The package you are using will give you all this information the moment you run your model. Yesterday, we demonstrated how to run the model. Once you run it, you see all this particular description. However, because of our time, we won't be able to discuss all this in detail, but rather we'll refer all to our earlier videos that already discussed the describing classifier errors in more details. What is the meaning of true positive? This is the one you would predict to be true, but it's actually true. False positive is when you predict something to be positive, but it is actually false. You see, like you say someone is sick, meanwhile it's not sick. True negative, you said it's not sick, and actually it's not sick. It's a correct one. False negative is the one that is not wanted in medical. You say someone is not sick, meanwhile it's sick. These are very important parameters that we want to see. How is your algorithm performing in this case? Of course, the recall, precision, F-measure, accuracy, they are. Once you get true positive, all these value out, you can easily calculate the other ones. What are the implications of all these ones? Like I said, we can always refer back to earlier videos. So, and this is how you locate your true positive. This is called confusion matrix, by the way. Yeah, very important to mention it. Confusion matrix can show you visually how the result is, how the system is performing. You can see here, this is, down here is the true value. Horizontal here is the predicted value. So it means this is positive, this is negative, originally from the data given. But this is the outcome from my model. So you can see here, we are expecting true positive. This is the true positive here that has been predicted. So as we're going to see an example shortly. Look at this example. We want to predict if somebody should buy something or not. The original, this is the predicted class, this is the actual class that was given to us. The label, remember the label. But this is the output from our hypothesis function that we have built. So this is buy, don't buy. You see, it should buy, but it's predicted no buy. So you see some will be mistaken. This is an error. There's no error here. This is an error. Yeah, there's a mistake here because the output is supposed to be buy, but it says don't buy. Here, it is yes. Because the answer is supposed to be don't buy, it predicted is going to buy. Maybe you want to predict the customer that's going to buy from you. You can try to understand the mode of your customer before they arrive in your shop or at your shop. So if you notice a customer is not going to buy, you don't try to see what can I do to make my customer buy my product. You see, these are some of the areas that the business people, they employ machine learning. Now, so now this is, so for the multi-class classifiers, typically because it's not two, you have to calculate the number of correctly classified divided by the total image. For example, if you are dealing with image classification and it's extendable to any other application. So when you have multi-class problem, this is the kind of confusion matrix you are going to have. You can see here you have DNA. How many DNA? 98 DNA are correctly predicted as DNA. Why 2 DNA were mistakenly pushed to ER? This one, all the ER are correctly predicted. You can see 100. And it goes like that. The one with mistake, you are going to see that there will be extra for A. This is the mistaken one. This is the output from classifier, where this is the true value from the label we were provided with. This is called confusion matrix. Now, sit on the model of evaluation. Now let's look at this particular example we have done. So this is the actual class. So 4 people were supposed to actually buy, and naturally they were predicted to have bought it. But one guy were predicted not to buy, even though they actually bought the product. This is where the first positive, the first negative, these lines are the error that can come in there. These are the error values. Why these are the correct ones? True, this is the true positive, this is true negative. True negative and true positive are correct result. So if I want to calculate the percentage error, it's going to be 4 plus 3 divided by the total summation. 4 plus 1, 5 plus another one, this is going to be 10. It's going to be 7 divided by 10. You take it to percentage, that's going to be the percentage accuracy of your classification. So yesterday when we used Wika, you can see 93%. That was how we got the 93 from Wika. You see, the package does everything for you. This is just for clarity for the members. Now, and for further detail, like I said, you can always revert back to our earlier. This is the example we've done here. It's just a simple mathematical computation of the error we have done. Where is it that the output is where is it that the outputs and the hypothesis function? This is the original output given to you. This is the hypothesis function, the prediction from your model. How are they different? This is the error. You sum all the differences where they are not equal. The prediction is different from the actual expected value. And then this is the error. This is the other way around. You want to know the error, it's going to be 3 out of 10. Remember I told you the correct thing was 7 out of 10. So the error is actually 100 minus the accuracy. Like yesterday, we got 93%. So the error is going to be 100 minus 93, which is going to be 7% error. This is how we calculate for classification. For regression in its own, because it's totally different, you are trying to predict actual value. How much are they actually touching it, as the case may be. This is the value we expected, and this is our model. It's not touching all of them. So what is the difference between how far is my model to those values? This is for regression. That's why we have a lot of evaluation measures for regression problem, like the mean absolute error, mean square error, mean absolute percentage error, mean percentage error, root mean square error, coefficient of dissemination, and host of others. And sometimes also we support our prediction with plots like this. We want to see what is the actual data. This is the actual data. How is my model? This is my model. It's going straight. How many am I able to touch? Sometimes you see some model that will touch all the points you are expected to touch with only few mistakes. And that will be determined by the error measure that we have reported here. These are all about how to evaluate our different models. Now, I think on that, we are going to have a little look into, we are going to have a little look into weaker numbers again to actually demonstrate this concept we just explained to us and hopefully make it even more understandable and clearer. So please hold on, and then while we shift to the weaker.